The systematic decommissioning of the Ticonderoga-class guided missile cruisers represents a seismic shift in the United States Navy's carrier strike group architecture. For decades, the TICO has served as the indispensable Air Defense Commander, ADC, housing the sprawling Combat Information Center facilities required to coordinate a fleet-wide umbrella against complex aerial threats. Unlike the Arleigh Burke-class destroyers, which are optimized for multi-mission flexibility and independent operations, the Ticonderoga was built specifically to manage the saturation of the battle space. The retirement of these hulls creates a vacuum in dedicated command and control infrastructure that current destroyer variants are still struggling to fill. A critical technical concern in this transition is the net loss of vertical launch system magazine depth. Each Ticonderoga-class cruiser provides 122 VLS cells, a capacity that far exceeds the 96 cells found on the Arleigh Burke Flight III. In high-attrition environments, such as those analyzed during recent operational audits, this magazine deficit limits the fleet's ability to sustain prolonged defensive volleys against massed anti-ship missile salvos. The Navy is now forced to explore the integration of large unmanned surface vessels, LUSV, to act as external missile magazines, attempting to restore the firepower lost with the cruiser's retirement. The Arleigh Burke Flight III is currently the primary bridge to the future, centered around the AN/SPY-6V1 Air and Missile Defense Radar, AMDR. This sensor suite is significantly more powerful than the legacy SPY-1 found on the Ticonderoga, offering enhanced sensitivity and range. However, the Flight III is a maxed-out design. Its hull lacks the growth margin for significant future upgrades in power generation and cooling. While it succeeds as a sensor platform, it cannot replicate the Ticonderoga's spacious command facilities, forcing a redistribution of the Air Defense Commander's staff across the strike group. The long-term solution lies in the DDG-X program, which moves away from the constrained destroyer hull toward a larger, more modular platform reminiscent of a cruiser's scale. The DDG-X is designed with an integrated power system, IPS, capable of generating the megawatts required for future directed energy weapons and next-generation railguns. This platform aims to reclaim the role of the Large Surface Combatant, LSC, by providing the physical space and electrical throughput that the Arleigh Burke hulls lack. It represents a strategic admission that high-end naval warfare still requires the displacement and magazine mass originally pioneered by the Ticonderoga-class. Technical audits following recent high-intensity simulations, such as Operation Epic Fury, highlight a grim reality. The current fleet's defensive endurance is tied directly to VLS cell count. During these engagements, the high expenditure of standard missiles, SM-2/SM-6, to intercept ballistic and cruise missile threats pushed logistics to a breaking point. Without the Ticonderoga's massive internal magazine, destroyers are forced to cycle out of the combat zone more frequently for pier-side reloading. This creates a maneuver vacuum where the carrier remains vulnerable, a gap that was previously mitigated by the cruiser's sustained stay time in the theater. The future efficiency of the U.S. Navy hinges on its ability to integrate a hybrid fleet that combines the high-end sensors of the DDG-X with the distributed lethality of unmanned platforms. The decommissioning of the Ticonderoga marks the end of the standalone supercruiser era and the beginning of a networked approach to air defense. Success will not be measured by ship count alone, but by the integrated operational availability of sensors and shooters. If the DDG-X fails to deliver on time, the Navy risks fielding a hollow mass surface force, plentiful in hulls, but critically short on the command depth and missile density required to survive a peer-level conflict.